Enthalpy, delta H, measures only change in enthalpy, or the transfer of heat. It is the difference between the potential energy of the products and the reactants. So it doesn't matter which path you take to go from the reactants to the products. It only depends on the start and the ending point. Because it only depends on the products and the reactants, it is a state function. When enthalpy is at a constant pressure, delta H is the same thing as Q, heat transfer. So our internal energy equation becomes delta U equals delta H plus W. So here we have a strip of magnesium, which has a mass of 15 grams, is dropped into a beaker of dilute HCl. What work is done under surrounding atmosphere at 1 atm and 25 degrees Celsius? So the first thing we need to write is a correct balance equation. So Mg is going to react with HCl. This is going to be a single replacement because it's the element and compound. Magnesium is a metal. It's going to replace the hydrogen, which will behave like a metal because it's in the front. So magnesium new partner is going to be Cl. The charge of magnesium is 2. The charge of Cl is 1. Crisscross plus H2, which is a diatomic. So we need to balance it. So we have to have a 2 in front of HCl. Since the formula of work is equal to P delta V, in order for the volume to change, the work must be done by the gas. The gas in this equation is hydrogen gas. Since we have 15 grams of magnesium, we need to use stoichiometry to calculate the moles of H2. So 15 grams of magnesium, diagonal units have to be the same. Grams of Mg, grams of Mg. We need to do molar mass here to calculate the moles of Mg. And there are 24.30 grams of Mg in 1 mole. The diagonal units cancel out. Moles of Mg, moles of Mg. This is mole ratio. This is the only time we could change from one element compound to a different one. So in the balance equation, there is a coefficient of 1 in front of Mg and a coefficient of 1 in front of H2. So the mole ratio is 1 mole of H2 over 1 mole of Mg. Multiply the top, multiply the bottom, and divide equals 0.617 moles of H2. In order to calculate the work done by the hydrogen gas, we need to find the volume. Since the pressure and temperature is given, we know that PV is equal to nRT. So here at this point, you could plug in for P and RT and calculate the V, or we could substitute in. We know that work is equal to P delta V, which is also equal to nRT. So N is the number of moles, 0.617 moles of H2. The gas constant is 0.08206 atm liters moles Kelvin. Temperature is 25 degrees Celsius plus 273 to convert into kelvins. And if you do the math correctly, you should get 15.1 atm liters. We want this in units of joules. 15.1 atm liter. 1 atm liter is equal to 101.3 joules. So this will equal to 1529.63 joules. The number of sig figs, there should be 2 because of the 15 grams. So 1, 2, I like 1 to the right. The 5 stays, so this is going to be 1500 joules. The work is done under surrounding. We know this is going to be a negative. so negative 1500 joules. Here we have acetylene C2H2, and it's combusted, and it has an enthalpy of negative 1255.5 kilojoules per 1 mole of C2H2. They want to know how much PV, which is work, done in kilojoules, and what is the value of delta U, or internal energy, for the reaction of 6.50 grams C2H2 at atmospheric pressure. So the first thing is we need to find delta H, because we don't have 1 mole. We started with 6.50 grams of C2H2. So starting with 6.50 grams of C2H2, we know that 1 mole of C2H2 is equal to 26.036 grams of C2H2. This is a molar mass of C2H2. It produces 1255.5 kilojoules of energy, which equals negative 313 kilojoules. We could calculate work. Work is equal to P delta V. The pressure given here is atmospheric pressure, so that's 1 atm. And they gave you the change of volume as negative 0.80 liters. This is equal to negative 2.80 atm liters. And we need it in joules, so we're going to convert. So negative 2.8 atm liters. There's 101.3 joules per 1 atm liters. And since this is in kilojoules, we're going to convert this into kilojoules. There's 1000 joules and 1 kilojoules. This is equal to 0.2836 kilojoules. So the internal energy is delta U is equal to delta H plus work. The delta H was calculated as negative 313 kilojoules. Here the work is going to be positive because the volume here got smaller and went negative. To get smaller, surrounding has to do work on the system. So this is going to be plus 0.2836 kilojoules, which equals negative 313 kilojoules. Here we have potassium hydroxide that is added to water, and so it becomes solid to aqueous. This is an exothermic equation. The energy is found on the product side. When energy is on the product side, it's exothermic. When it's on the reactant side, it is endothermic. So does the container get warmer or colder? Since it's exothermic, it's going to be warmer, and since it's warmer, it is exothermic. They want the enthalpy change for 14 grams because here it is for 1 mole. So we're going to start with 14 grams of KOH. Diagonal units have to be the same, grams KOH. So 1 mole of KOH equals to 56.105 grams of KOH. In this reaction, there's 1 mole of KOH, and that releases 43 kilojoules of energy. 10.7298. There should be 3 sig figs here. 1, 2, 3. So it's 10.7 kilojoules. Negative because it's exothermic and all the units cancel out. Pause the video, solve this problem, and then check your answer. Here we have 1 mole of methane, CH4, is burned at constant pressure. 890 kilojoules per mole of energy is released. So this is an exothermic reaction. But we don't start with 1 mole. We start with 5.8 grams of methane. So we need to calculate delta H. So we're going to start with 5.8 grams of methane. Diagonal units have to be the same. So grams CH4, and we're going to go to moles of methane, which equals to 16.05 grams of methane There's moles of methane. This is moles of methane. There's 1 mole in 890 kilojoules. This equals to 321.6 kilojoules. There are 2 sig figs because of the 5.8. So 1, 2, I look 1 to the right. So this is 320 kilojoules. And since it's released here, I need a negative. It's an exothermic reaction. In this problem, we have barium nitrate that is mixed with sodium sulfate. It forms a precipitate, barium sulfate. So this is a Q reaction that is equal to Q solution. So what's happening is we're mixing two things at the same temperature. Energy is released and new compound is formed. So this is going to equal to MC delta T. However, the mass is not given, but the volume is given. So what we need to do is we need to add these together because at the end, the volume is additive. So we're going to add 1.0 liters of the barium nitrate, which is 1, and then 1 liters of sodium sulfate. Density of the solution is given as 1 gram per ml. I could find the mass of the solution using dimensional analysis. We first need to convert the liters into milliliters because the density is given in milliliters. So there's 1 liter is 1,000 milliliter, and 1 milliliter is 1 gram. The solution, when it's mixed together, has a capacity of 4.18 joules per gram degrees Celsius, and my temperature final was 28.1 degrees Celsius minus my initial, which was 25. This equals 25,916 joules. So if I calculate the moles of the solution, we have 1.00 liters, and you could use either one because the volume and the molarity is the same. So 1 liter barium nitrate to 1 mole of barium nitrate. So there's 1 mole for the reaction. So if I divide this by, so it's 25,916 joules per 1 mole. If I convert it into kilojoules, this is going to be 1,000 joules and 1 kilojoules. And with sig figs, it should be negative 26 kilojoules per mole. And again, it is negative because heat was released to increase the temperature. Pause the video, try this problem on your own, and then check your answer. This problem too is similar to the previous one. We are mixing sodium hydroxide with hydrochloric acid. They both start at the same temperature of 24.6 degrees Celsius, and their final temperature is 31.3 degrees. So we know the Q of the reaction because that's what they want. The enthalpy change for the neutralization is equal to Q of the solution. And we know Q of the solution is MC delta T. And the solution, the mass has to be additive. So we have 100 milliliters of the sodium hydroxide plus 100 milliliters of the hydrochloric acid. Needs to be converted into grams. Density is provided as 1 gram per cubic centimeter. So we know 1 ml is equal to 1 centimeter cube, and 1 centimeter cube is equal to 1 gram. My C is given as 4.184 joules per gram degrees Celsius. My temperature final is 31.3 degrees Celsius minus 24.6 degrees Celsius, which equals 5,606.56 joules. So to find the neutralization for the reaction, we need to figure out the moles. It doesn't matter if you start with the sodium hydroxide or the hydrochloric acid because since they have the same volume and molarity, there is no limit here. So I'm going to start with 100 milliliters of NaOH. I'm going to convert my milliliters into liters because molarity is always in liters, and 1 mole per 1 liter. This is equal to 0.1 mole. So to find the moles per mole, 5,600.6 joules per 0.1 mole. And we could convert this into kilojoules. There's 1,000 joules in 1 kilojoules. This is equal to 56.07 kilojoules per mole. And it again is negative because heat is going up the final temperature, so heat is being released. Enthalpy of formation, or delta HF naught, is the little degree symbol. It's the same thing as enthalpy. It is the production of 1 mole of compound from its elements. The most important thing is its elements in their standard states. And when it's in standard state, we use this degree sign or naught sign. Elements in standard states are at 25 degrees Celsius, 1 atm, or 1 molar. When that is true, our delta HF naught is always equal to 0. So if hydrogen is labeled as a gas on the periodic table at room temperature, it is a gas at room temperature and 1 atm. So the value of that is 0. The equation just becomes delta HF naught is equal to the sum of the moles times delta HF naught of the products minus the sum of the moles times the delta F naught of the reactants. So here we're going to determine the delta H naught reaction for the following reaction. So all of these values will be provided for you unless they're elemental state. So if they are in the standard elemental state, you should know it has a value of 0. So for example, here, aluminum at room temperature is a solid, so the value is going to be 0. And that's the only one that's going to cancel out. So now I write my equation. General equation is delta H of the reaction here is going to equal to the summation of a delta F naught of the products minus the summation of the moles times the delta F of the reactant. So we know that everything on the right of the arrow is the product, anything left of the arrow is the reactants. So here my equation is going to be the moles of Al2O3 solid delta HF naught of Al2O3 solid plus the moles of AlCl3 solid delta HF naught of AlCl3 solid plus the moles of NO gas delta HF naught of NO gas plus the moles of H2O gas times delta HF naught of H2O gas. The states of matter are very important in these problems because the values change. Minus the reactants, which is the moles of ammonium perchlorate, delta HF naught of ammonium perchlorate. So again, all these values will be given to you unless you're solving for it, but the elemental states you need to know. The moles of aluminum oxide, since the coefficient is 1, there's only 1. If you look this up in your textbook, the value for aluminum oxide is negative 1676 kilojoules per mole, plus the moles of aluminum chloride. Again, coefficient is 1, so I put 1. The value of that is negative 704 kilojoules per mole. There are 3 moles of NO, so I need to put 3. The value of NO gas is positive 90 kilojoules per mole. The next one is water. Water, there are 6 of them, and it's the gas value you want and not the liquid. it is negative 242 kilojoules per mole, minus our reactant here. There's 3 moles of that because the coefficient is 3, times the value, which is negative 295 kilojoules per mole. So if you do this correctly, negative 2,677 kilojoules per mole for the reaction. It's an exothermic reaction. If you did not get negative 2,677, double check your signs. So if you look at your signs, this one will come out negative, this one will come out negative, this one is positive, this one will be negative, and this one will be positive. So double check your signs. Pause the video, try this problem on your own, and then check your answer. This problem is similar to the one above, so we're going to do delta H, the reaction. This is going to equal to the summation of the moles times delta H F naught of the products minus summation of the moles times the delta H F naught of the reactants. Already we could cancel out 1, which is oxygen, because oxygen is gas at room temperature and at 1 atm. So the value of O2 will be 0. Here our equation becomes the moles of CO2, delta H F naught of CO2, plus moles of water, delta H F naught of water, plus minus the moles of glucose times the delta H F naught of glucose. Here, the heat of reaction is provided for you because the heat is given as 2800 kilojoules. It is on the product side, so this is an exothermic reaction. So when I put this in, this is going to be negative 2800 kilojoules for the heat of reaction. So we are looking for glucose. So the moles of CO2 is coefficient is 6, so I put 6. The delta HF is negative 393.5 kilojoules per mole. The moles of water, there's 6 moles. Value for water is negative 285.8 kilojoules per mole, minus the moles of glucose, which is 1, times delta HF naught of C6H12O6. After you calculate, so delta HF naught of glucose becomes negative 1,276 kilojoules per mole. If you are not getting these answers, double check your math. Delta H is exothermic, so you have to put a negative sign because the energy is found on the product side. This is negative. This is negative. So when you move it to the opposite side, they become positive. And then you must carry the negative through. For heat of formation, all the values will be given to you, or you need to solve for it, except for the elemental states. The elemental states, you need to note that it is equal to 0. Hess's law is a change in enthalpy. Instead of occurring in one step, it occurs in a series of steps. So that means 2 or more. What you do is you rearrange the steps to look like the original equation. When you reverse the reaction, you need to reverse the sign of delta H. If you multiply and divide one of the steps, you must multiply and divide the delta H by the same amount. And at the end, you total all the sum, and that will be your enthalpy change for the reaction. So here we're calculating the delta H for the following equation. This is the original equation. This equation occurs in 3 small steps, or 3 series of steps. So what we do is we rearrange the equation and cancel out things that are not in the original equation to get the original equation. Step 1, which is H3BO3. If I look at my original equation, the H3BO3 is on the left side, so I leave it as is. And so I'm going to rewrite it as is. Since I made no changes to my equation, my delta H is also going to remain the same. So the middle equation is difficult to determine if it should stay or flip. But I could look at my final equation, the third equation down here, and we know this equation has to stay as is because the B2O3, the B2O3 are on the product side. So I'm going to recopy the third equation. And since we made no changes right now, I'm going to leave my delta H as is. So now let's look back at my middle equation. I have H2B4O7 on the reactant side, but it does not appear in the original equation. So that means the second equation, the H2BO7, must be on the product side for the H2B4O7 to cancel out. So I'm going to flip that equation. So that's going to be 4HBO2. Since I flipped it, I need to change the sign. So it's no longer negative, it's going to be positive 11.3 kilojoules per mole. So now I'm going to add these. So I need to multiply the first equation by 4 in order for the HBO2s to cancel out. So when I do that, there's 4 here, and 4 here. So these cancel out. So that means I also have to multiply the delta H by 4. Next, the H2B4O7s cancel out. The rest stays. So if I write this down, this is 4H3BO3AQ yields 2B2O3 solid plus there's 4, 5, 6 waters, 6 H2O liquid. So after I multiply 4 times negative 0.02 and I add all these numbers up, you should get positive 28.72 kilojoules per mole. But if you notice, the equation doesn't look the same. I have to divide the entire equation by 2. So when I do that, I divide that by 2, this by 2, this by 2. That means I have to divide the delta H by 2. So this is now 2H3BO3 yields B2O3 plus 3H2O. You have to rewrite the equation. And this becomes 14.4 kilojoules per mole. The answer came out positive, so this is endothermic. There is one place after the decimal because you line up the decimal. So look at the original problem, rearrange the steps to match the problem. You want to rearrange the steps you know for sure are in the right order, because that way it will help you arrange the other ones that could go either way. After you simplify everything to get your final answer, make sure the coefficient matches the coefficient of the original equation. If you divide the coefficients out, you need to divide the delta H out. If you multiply the equation, you must also multiply the delta H by the same amount. Pause the video, try this problem on your own, and then check your answer. So here we have the original equation. Methane reacts with ammonia. And so if it occurs in three steps. So the first equation, we need to flip why the ammonia is on the left side. So we need to make sure the ammonia is on the left side. Since we flipped the equation, my delta H is now positive 91.8 kilojoules. The second equation, the H2 is on the product side, but this one, the H2 is on the product side. Methane is on the reactant side, and we know that for sure, so we know we have to flip this equation. Since we flipped the equation, we have to change the sign, so this is positive. The last equation will stay as is. If I look at my equation, graphite is not in the original equation. Since the second equation had to be flipped because the methane had to be on the reactant side, the graphite is now on the product side. To cancel out the graphite on the product side, the third equation has to have the graphite in the left side. In addition, HCN is on the product side in the original equation. So we're going to just recopy this as is. Since the equation was not changed, I'm going to leave the delta H as is, and it's going to remain positive. Now we're going to simplify this equation. So the middle equation has to be multiplied by 2 to cancel out the graphite. So when I do that, we have 2 methanes, 2 graphites, 4 hydrogen, and then I need to multiply my delta H by 2. When I do that, the graphites cancel out. The N2s cancel out. We have an N2 on the product side and an N2 on the reactant side. 3 H2s plus 4 H2, that's 7, and 1 on the opposite side. So this one now becomes 6. So now I'm going to rewrite my equation. So that's going to be 2 methanes plus 2 ammonias yields 6 H2 plus 2 HCN. I get 511.9 kilojoules. To make the equation look exactly like the top one, I need to divide everything by 2. To make my equation look like the top one, I need to divide everything by 2. Even the delta H. So when I do that, I get 256.0 kilojoules. One place after the decimal. This becomes 1, this becomes 1, this becomes 3, and this becomes 1. We need to rewrite the equation. So Hess's law is really easy. You just rearrange the equations to look like the original equation and just simplify. And you need to do the same thing with the delta H. If you flip it, you need to change the sign. If you multiply by a factor, you need to multiply by the same factor. If you divide by a factor, you need to divide by the same factor. And make sure you keep track of your signs. Since this came up positive, this is an endothermic reaction.